KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, our concentration is towards movement of inertia. Movement of inertia, which is a very, very important topic. For example, regarding the board point of view or otherwise for competitive point of view also, movement of inertia is important topic as well as in our daily life also. Okay, right. And regarding this moment of inertia in this class, we are going to discuss the calculation of moment of inertia also, right? And in this class, our interest is moment of inertia and calculation of moment of inertia. Afterwards, radius of gyration. Radius of gyration. Okay, right. First, I want to explain the importance of moment of inertia in our daily life. We are seeing different shaped bodies in our life on this planet. Snake. If you see that the head is like little bit very small for seeing. Okay. When it is going to eat, it will become very big. That will be different. Just for seeing in normal position, the head is like a small thing, and the middle part is like somewhat big, and tail is very small, right? That is the structure of snake. If you see the human, head, then two hands, and then central part, and then two legs, right? This is the part of a human, right? And if you take a train, so it is almost like similar from starting to ending, right? So if you see the car, right? So ambassador car, how is it, right? So the middle part is somewhat more thickness or mass, space, okay? And the front part is less, and front part is almost equal to back part in case of ambassador car, so olden days, right? So either in case of living beings or non-living beings, the distribution of mass, I am talking about distribution of mass, right? It will be different. It will be different from one body to another body, okay, right? And in case of translatory motion, in case of translational motion, that's what we discussed in the chapter of laws of motion, in the chapter of motion in a straight line, right? In the chapter of motion in a straight line, we discussed that is what translatory motion. Okay, so a body is moving along a straight line. Okay, and in the laws of motion chapter, Newton's first law of motion, we got a new physical quantity, that is what new and main, that is what inertia, right? And mass is the measure of inertia. Mass is the measure of inertia. You just for 1 minute, you just keep in mind what is inertia. What is inertia, right? Inertia is actually the unwillingness of an object to change its state, right? Suppose for example the body is at rest, means to go from rest to motion, it requires and it needs the external effort. That nature of body is called as inertia, right? So inertia is the unwillingness of an object to change its state. State means you have to keep in mind state of rest and state of motion and state of direction, right? These three things come into the picture, right? So in case of translational motion, the unwillingness of an object to change its state, right? That is what we are calling it as inertia. And one more very important thing is mass is the measure of inertia. Mass is the measure of inertia. Okay, right. So this is about translational motion or translatory motion or straight line motion. Okay, right, whatever it may be, right. Now we are in the chapter of rotational motion. No, so what about the rotational motion? What about the rotational motion, right? It is similar. So this moment of inertia is similar to the mass in translational motion, right? And I already told you inertia is the mass is the measure of inertia. Mass is the measure of inertia in case of, that is what, translational motion, right? So here moment of inertia and there mass or inertia in case of translational motion. Okay, that we have to notice, that we have to identify, right? That's what I want, that's what I am saying from starting of this class. That is what moment of inertia, right? Moment of inertia. Okay, right. From starting of this chapter I am saying, you compare, whenever the situation comes in this chapter, you just compare with translational motion, then you can understand easily, right? The concept will become very easy, right? So this entire chapter, our concentration is rotational motion, right? So rotational motion is one kind of motion, same like translational motion, right? So we have translational motion, circular motion, and in future you will get oscillatory motion, right? And wave motion. Like that, rotational motion is also one of the type. There may be somewhat complications, but anyhow it is a type of motion. So whenever the situation comes in rotational motion, a new situation comes. For example, here moment of inertia is a new situation, but it is available in rotational motion and it is analog. It is analog of mass in, okay, it is analog of mass in translational motion. Okay, that's what I want to say to understand easily. Okay, right. So to see here, see the first sentence, that is what is the analog of mass in rotational motion? What is the analog of mass in rotational motion? Okay, so that's what the answer is. We know that for a body rotating about a fixed axis, what is rotational motion? How a body is rotating? That's what we already discussed, right? Rotational motion means, for example, okay, the best example is potter's wheel, otherwise fan, right? You can imagine axis of rotation. Where is the axis of rotation, right? So based on that, the body is rotating. Okay, right. So what about the particles of the body, right? And how they are rotating around a fixed axis. And what about the angular velocity, and what about the angular displacement, and what is the relation between linear velocity and angular velocity, right? So that and all we discussed. So see here, for a body rotating about a fixed axis, each particle of the body moves in a circle with linear velocity given by v is equal to r omega. Because of that is what the number of particles are there now. For example, if you know that is the particle is ith particle, vi is equal to omega into ri. Vi is equal to omega into ri. Okay, that is what the relation between linear velocity and angular velocity. Okay, right. For a particle at a distance from the axis, the linear velocity is, okay, that is vi is equal to omega into ri. Vi is equal to omega into ri. And next thing, okay, right. So again he told the same thing. That is what he already told. Next, see here, the kinetic energy of motion of this particle. The kinetic energy of motion of this particle is Ki is equal to half mi into vi square. So it is the formula we are using in case of translational motion, right? Here we had this relation vi is equal to omega into ri, means we have to understand there is a link. There is a link between the linear velocity and angular velocity. Here, a particle which is in rotational motion is experiencing and is exposing to the both, that is what linear velocity and angular velocity, right? And at particular instant of time, if you want to find its linear velocity, you can, that is what just by knowing the angular velocity and its position vector from the axis of rotation, you can find out the linear velocity, and the direction of linear velocity is tangent drawn to the point. Tangent drawn at the point. At the point means where the particle is present. Okay, right. The kinetic energy of motion of this particle is Ki is equal to, for ith particle, the kinetic energy is Ki is equal to 1 by 2 into mi vi square, right? And we are writing this value, that is what 1 by 2 into mi r I square omega square, r I square omega square. That is what kinetic energy of motion of this particle, right? Mi is the mass of the particle. Mi is the mass of the ith particle, right? Now, the total kinetic energy K of the body is, the total kinetic energy K of the body is then given by the sum of the kinetic energies of individual particles, is then given by the sum of the kinetic energies of the individual particles, right? So, the same expression he is extending to the whole body. So, then K is equal to sigma I is equal to 1 to n Ki, sigma I is equal to 1 to n Ki, that is equal to 1 by 2 into sigma I is equal to 1 to n. In place of Ki, he is writing mi r I square omega square. Okay, right. Here n is the number of particles in the body, number of particles present in the body, right? And if you observe carefully the rotational motion of your body, omega is same for all particles. Omega is same for all particles. So that you can take omega is outside of the expression sigma, no? Then it will be like this. You can write, when you are taking omega is also outside, you can write like this: K is equal to 1 by 2 omega square, K is equal to 1 by 2 omega square into sigma I is equal to 1 to n mi r I square, mi r I square. Okay, right. Here after writing this, that is what K is equal to 1 by 2 omega square into sigma I is equal to 1 to n mi r I square, you can define a new parameter. We define a new parameter characterizing the rigid body called the moment of inertia, I, given by I is equal to sigma I is equal to 1 to n mi r I square. With this definition, K is equal to 1 by 2 I omega square. K is equal to 1 by 2 I omega square. Okay, right. Note that the parameter I is independent of the magnitude of the angular velocity. I is independent of the magnitude of the angular velocity. He is not talking about K, it is what he is talking about I. I is independent of the magnitude of the angular velocity. Okay, right. It is a characteristic of the rigid body and the axis about which it rotates. So, in these two lines of information, he is talking about the dependency and independency of moment of inertia on other factors. Okay, right. See this here. These 2 points are important for conceptual bits from rotational motion chapter regarding NEET and mains. Okay, right. So, is very important. I is independent of magnitude of the angular velocity. It is a characteristic of the rigid body and the axis about which it rotates. That is what axis of rotation. Axis of rotation. Okay, right. And we can compare the above with K is equal to half mv square. This one you can compare with K is equal to half mv square, right? That is what this equation is the kinetic energy. This is the kinetic energy of a rotating body with the expression for, right, this is for kinetic energy for a body in translational motion. If you compare these two, what can we write, right? And already we know that is what V is equal to R omega. V is equal to R omega, right? So if you compare that, you may conclude that I is equal to mr square. That we will get it in the same class, I will tell you, right? But till that you have to remember, if you compare these two, you will get it as I is equal to mr square. I is equal to mr square. Okay, right? And m is the mass of the body and v is the velocity of the body, right? And we already told you that we already discussed, that is what analogy between angular velocity and linear velocity, that is what v is equal to r omega. V is equal to r omega, right? And I already told you in the same class, that is what moment of inertia is the rotational analog of mass. Moment of inertia is rotational analog of mass. And in rotation, the moment of inertia plays a similar role. In rotation or rotational motion, the moment of inertia plays a similar role as mass does in linear motion. Okay, right? And now we are going to calculate the moment of inertia. That is what a practical situation, right? So calculation of moment of inertia, right? And you see here, that is what when we are going to calculate the moment of inertia, right? That is different for different bodies. Different bodies means, for example, it is what it is what iron rod, for example a square plate, for example a rectangle plate, cylinder, right? Circular shaped body, triangular shaped body, right? We have various types, various shapes of bodies, right? So whether it is living or non-living, that is different situation, right? That's why to calculate moment of inertia, we have to take one example, right? Here we are going to take a thin ring of radius r. I hope you are able to imagine a thin ring. I think girls are used to play, that is what, ring ball something, right? So that's why you just imagine what is a thin ring. Consider a thin ring of radius capital R and mass capital M, rotating in its own plane around its center with angular velocity omega. Right? Each mass element of the ring, so that whole mass of the ring, you just imagine in smaller and smaller elements. Okay, smaller and smaller elements. Each mass element of the ring is at a distance capital R. From the axis and moves with a speed r omega. That is what V is equal to r omega, no? That is only, right? Now, the kinetic energy is therefore. So what is the formula? What is the kinetic energy, right? The basic formula is of mv square. And if you write V is equal to r omega, 1 by 2 m r square omega square. Compare this, you compare with k is equal to 1 by 2 I omega square, right? That is what I is equal to mr square. This is what the moment of inertia in case of thin ring of radius r. Okay, right? And one important point I need to say here, that is what moment, I already told you, moment of inertia is not same for all shaped bodies, because the bodies having different shaped means the moment of inertia will be different. And if you change the axis of rotation, for example, you take the mobile, how many ways you can rotate? right? So you just imagine, right? So vertically, horizontally, and by taking the corners as a, set axis of rotation, right? In many ways you can rotate now. So when you are changing the axis of rotation, the R value changes, then automatically moment of inertia will be changed. That's why we cannot say this is the moment of inertia for this body, because it depends upon the that is what axis of rotation, and here mass also, that is what m and r square, right? So that's why in case of thin ring of radius, it is I is equal to m r square. Okay, right. And now we are going to take another example, that is what see here. This is a light rod of length L with a pair of masses rotating about an axis through the center of mass of the system and perpendicular to the rod. So total mass of the system is m, right? Total mass of the system is m. Okay, so here there are two masses, this is what m by 2 and this is what m by 2, and it is very thin light rod which connects these two masses, and the mass of the whole system is obviously it is m only, and because of the thin light rod we are neglecting the mass of this, and this is the axis which is passing through the center of the rod, and automatically it is L by 2 and it is L by 2 when L is the length of the rod, okay. So this is our next example to discuss moment of inertia, okay, right. And this rod is a rigid one, right? So this is a rigid massless rod of length L with a pair of small masses m by 2 and m by 2 rotating about an axis through, see along the light rotating about an axis through the center of mass perpendicular to the rod. Each mass is m by 2 is at a distance L by 2 from the axis, okay, right. So now the moment of inertia of the masses, wholly, that is what the whole system you consider, the moment of inertia of the masses is therefore given by, that is what first for this one m by 2 into L by 2 whole square plus for this m by 2 into L by 2 whole square. That's what we can write, okay. Thus for the pair of masses rotating about the axis through the center of mass, through center of mass and perpendicular to the rod, I is equal to m L square by 4, right? You do this calculation, this you will get it as m L square by 4, which is what m by 2 you can take it as out, and it is L square by 4, right? So m by 2 into L square by 4 plus L square by 4, if you do that means you will get it as m L square by 4, okay, right. So now whatever it may be, here a mass of the body resists a change in its state of linear motion, right? Once if you go back to the translational motion, there mass of a body opposes a change in its state of linear motion, right? And it is a measure of its inertia in linear motion, that is what in translational motion, right? So the similar thing here, similarly moment of inertia about a given axis of rotation opposes a change in its rotational motion, right? That's why it can be regarded as a measure of rotational inertia, right? So moment of inertia is a measure of rotational inertia in case of rotational motion of a body, okay, right. And it is a measure of the way in which different parts of the body are distributed at different distances from the axis, right? So that is what like this. So it is like a two particle system. So here also you can find the moment of inertia, and there is a single body which is rotating about an axis also you can find out that, right? So for whatever it may be, when there is a rotational motion, you can calculate that moment of inertia, okay, right. Unlike the mass of the body, right, the moment of inertia is not a fixed quantity, but depends on the orientation and position of the axis of rotation with respect to the body as a whole. So just now I told you, moment of inertia depends upon the axis of rotation and orientation of the body. So in which direction how the body is going to move, how the body is going to get the rotational motion. Okay, right. As a measure of the way in which mass of rotating body is distributed with respect to the axis of rotation. Okay, that is what so the mass of a rotating rigid body is distributed with respect to the axis of rotation. Okay, he is talking about the dependency and independency of moment of inertia. Okay, and here itself we can define a new parameter, that is what radius of gyration. Okay, so what is radius of gyration? So actually, as simple as such, radius of gyration I is equal to, okay, so the same, that is what right. So whatever it may be the symbol, generally we are using a K. Radius of gyration means here, that is what okay, K. And if you observe carefully, here if you observe carefully, I is equal to mr square. Similarly, you can write it as I is equal to mk square. But what is K here? Right? That is very important. For a rod about the perpendicular axis at its midpoint, K square is equal to L square by 12. That is, K square is equal to L by root 2. Square root of 12. Right? It's okay, it's not a problem, because I already told you based on the position of axis of rotation, right, and distribution of mass, right. So this value of moment of inertia will change, right. So based on that axis, that is what radius of gyration also depends. That is not a problem, because it is different for different shaped body, and it is different for different axis of rotation also. But basically, what is radius of gyration? If you understood that, it is enough, because if you want, you can apply it to any body, right. See here, see this, see here the radius of gyration of your body about an axis may be defined as, the radius of gyration of your body about an axis may be defined as the distance from the axis of a mass point whose mass is equal to the mass of whole body and whose moment of inertia is equal to the moment of inertia of the body about the axis, right. So while when I am talking about radius of gyration, you keep in mind, when certain number of particles are there, when all particles are combined to make one body, right. So what is the difference? What is the difference? That you have to keep in mind. I will repeat once again here. The radius of gyration of a body, this definition is important. If you stress this definition, you can easily understand what is radius of gyration. Okay, the radius of gyration of a body about an axis may be defined as the distance from the axis of a mass point whose mass is equal to the mass of whole body and whose moment of inertia is equal to the moment of inertia of the body about the axis, okay, right. And at last I want to conclude, that is what I already told you. The moment of inertia of a rigid body depends on the mass of the body, its shape and size, distribution of mass about the axis of rotation and the position and orientation of the axis of rotation, right. So as simple as such, you remember, moment of inertia depends upon mass of the body, distribution of mass of the body around axis of rotation, and position of axis of rotation, shape, size, orientation of the body, right. Basically two things, one is mass, another one is position of axis of rotation, okay, right. So this is all, this is if you go for that is what dimensions of moment of inertia, it is ml square. By saying this, you can say ml square, and SI units are kg meter square, okay. And this calculating moment of inertia helps you a lot, right. In night clubs, in pubs, right, in some of the circuses, right? And you know, the person is going to bend. The person is going to bend, and you know, around a pole they are dancing, right? You know, how can we bend the body, right, without slipping, without skidding, right? Because when we are getting rotational motion, you know very well, you can suppose as yourself, if you want you can get translational motion, and if you want you can get rotational motion, right? So when you are dancing you may get rotational motion, right, sometimes. So when you are getting rotational motion, this idea of moment of inertia is very important, right, because it helps us to resist the change in state in case of rotational motion. Okay, right. Okay, so in this class we focused on what is moment of inertia, right, and basically what is the formula to calculate moment of inertia, and what are the factors on which moment of inertia depends, right. Then after by taking two examples we calculated moment of inertia, right. And after completion of that we discussed one more important factor, that is what, radius of gyration. Okay ma. So once you go through this, after completion of this video, once you go through the textbook also, I request you, once you go through the textbook, right, so if you have any doubts you can discuss through a platform, right, and with that you can get full clarity, right. So this chapter is important ma. This chapter also having weightage, right, regarding NEET and mains, and this chapter also helps us while solving the problems related to some other chapters. The idea of rotational motion is very important for us, and in this chapter this moment of inertia is also important. Okay, right. Thank you. We will continue in the next class.